Welcome to the bonus session of Opti 202, Next Level Modeling, Enhancing Optimization with Generative AI. And as everyone knows today that Generative AI is the hot topic and lots of effort, time, money, all sorts of things being invested into this technology. And it is something that is definitely exceptionally important for anyone particularly with the technology background to know and understand. So one of the things that you may do or see or something like that is a lot of us as practitioners or managers of such or taking classes or teaching classes on analytics material is we are going to we write a lot of code and one of the things that a lot of people tend to use generative AI for, something like ChatGPT, is to help generate that code. And I actually did a couple little informal surveys as I've done presentations on this, and a lot of people do that. So we at Gurobi, we thought, all right, this is an excellent opportunity to further promote the learning of mathematical optimization, also while using generative AI to help that and guide that. So I'm first going to sort of talk a little bit about the relationship between generative AI and mathematical optimization, and then dive into sort of how we're sort of merging the two to help people learn. So let's actually start with the question that some people may disagree on for the answer. Is mathematical optimization part of AI? Some will say yes, some will say no, some will be like, I don't care, I just want to solve optimization problems or whatever. But the answer is kind of important because there is a relationship between a lot of things that you think are part of AI and maybe not, and how generative AI also works within that. So let's start diving into that relationship. So let's not just ask ourselves if mathematical optimization is part of AI. Let's ask the oracle of today. Let's conversation with ChatGPT. So let's first use ChatGPT to help define intelligence. Because if we're talking about artificial intelligence, let's talk about intelligence. And essentially, a couple of the key things that pop out here is intelligence is something that applies reasoning, problem solving, adapting to new situations, making decisions, and achieving goals. If you've learned nothing else so far from Opti 101, 201, and what we've talked about so far in 202, is that mathematical optimization is exceptional at problem solving for combinatorial problems and the problems that you can translate, from your decision problem to the constraints, objectives, decision variables, and solve via code and get everything like that. It's also exceptional at adapting new situations. We continually add new scenarios to our problems and remove things and are editing the models. And it is great for decision making and achieving goals. So I would say so far that we are very much talking about things that mathematical optimization can do. But again, let's be very specific about our question here. Is mathematical optimization part of artificial intelligence? So, hey, taking into consideration what you just said, ChatGPT, what do you say now? And it says, yes, mathematical optimization is part of artificial intelligence. You can read the rest of the text, but essentially the part that I want to highlight is that optimization techniques are fundamental to AI processes for training machine learning models. We've talked about that, but also planning and decision making. And these are things that people do in AI, and mathematical optimization 100% meets that. So to take our first sort of stab at understanding this relationship, let's look at some of the let's look at all of the terms that sort of people use to describe AI and mathematical optimization and sort of see how they work together. You may hear a lot of predictive analytics, prescriptive analytics, and then also generative AI. And here is a nice visualization via Gartner on a recent research piece that explains that relationship and sort of shows some example scenarios of how predictive, prescriptive, and analytics work separately, work together, and then how if you enhance that with generative AI, how you get even more value. So let's look at one of the scenarios from this visualization here, where we're talking about prescriptive analytics only. That's something that is a very common use case of mathematical optimization, of optimizing a supply chain. And then moving down to number 3, when you talk about predictive and prescriptive together, using customer behavior predictions to tailor marketing. So you're using predictions to make decisions afterwards. That's an exceptional use case of combining the two. Then I'll go all the way down at the bottom to number 6, something that incorporates all of these different tools, prescriptive, predictive, and generative AI. It's integrating customer purchase prediction with real-time pricing, maximizing revenue, and so something like doing scenario generation or trying to understand the inputs and outputs at a completely new level. So the fact that that there's this research piece, and I'm going to talk about another one in a second, that combine all 3 of these things together under one umbrella really hints at the fact that mathematical optimization is in fact part of AI. But let's look at another piece. So another piece of Gartner research really sort of highlights the differences between the parts of generative AI, the parts of AI that are generative, parts are non-generative, and other techniques as well. And plus, they give a nice statistic that they've reached from a piece called "Go Beyond Machine Learning and Leverage Other AI Approaches" from September of 2023. And in that piece, they say 70% of organizations that rely solely on machine learning for AI initiatives will spend more money per solution than leveraging composite AI techniques. So going back to the previous slide of hey, you need to be using a lot of things together. That is the way to go. So generative AI may be the most important thing now, but in solving problems, you need to have a diverse toolkit. And sort of another visualization here that I really like is sort of talk about how AI is a broad space. You need to have a broad set of skills, in which optimization is one of those skills highlighted up on the top. So definitely make sure that you have, if you're trying to build a team, then all of these skills should be part of that team. Now that we've put that question to bed, let's see how we can use generative AI to help learn mathematical optimization, learn new use cases, expand your skill set here, and do it in a fun way that everyone nowadays knows how to do it. That's writing prompts and using generative AI to help us out. So our effort here at Gurobi to help people learn mathematical optimization using generative AI has sort of 2 parts. And the main part here of our effort is what we sort of see here. It's our whole effort we're calling Gurobi AI modeling, but one of them is a documentation site that helps you understand how these 2 things should work together, how mathematical optimization and writing prompts and understanding using generative AI to help you formulate models and write the code from a given decision problem that you have. So you have a problem statement, and then how can you take that problem statement and effectively get the right code that gives you the right solutions and the right formulation as well in between that. How does it all come together? So we have this repository here. The URL is on the slide. There's a QR code as well. This repository is very in-depth, and we're going to be adding to it a lot. There's already definitely new stuff that's on the repository, that's on this website that you don't see right here. But it talks about the difference between model writing and prompting, accessing our GPT that we've put together that I'm going to talk about in a minute, example prompts, good things, bad things to do, sort of a really good tutorial on how to use generative AI in the best way possible in order to learn and expand mathematical optimization. Now, since we are a little bit of the intermediate level, that's not, this may be something that you can use to help guide yourself and do a little bit more advanced stuff, but also share this with learners as well. The other part of our efforts here at Gurobi to, again, use generative AI to help people learn mathematical optimization is we have put together a slightly customized version of ChatGPT where we give ChatGPT a little bit of background saying that you are an optimization expert and you know Gurobi Pi, and given a problem description, here's how you respond. You first give a problem definition, you build and solve the model, and then you run the code, displaying solutions and everything like that. This is what we're calling Gurobi AI Modeling Assistant on the GPT Marketplace. So you can go and find it now. There's the URL. If you want to copy paste, there's a QR code. If you want to just search for it, it is there as well. So it is just a very simple adaptation of ChatGPT that we've put together. And also there is as you see in the GitHub repository, I put a couple files in there for next level modeling. You can see these links as well, but also custom templates for prompts, which is something we found to be pretty beneficial in terms of getting better results. So take a look at that folder in the repository, try out the GPT, try out the documentation, and let us know what you think. There should be a survey link in the documentation. Please, please, please take the survey. It's just a couple questions. Let us know what you think, and we will be continually improving the documentation. We'll also be improving this. We may be adding other GPTs as well to help with prompting or something like that. So there's still a lot for us to do here. So I want to very quickly go over what our effort is and what it is not. So if anyone's sort of, hey, why are you, this seems like you're going a little too far here or something like that. Again, I just want to quickly go over the yeses and nos of what we're trying to accomplish. We want to have a read the docs repository so people can learn hands-on very quickly and easily. It is not a way to do end-to-end model building for advanced applications. It aims to inspire people. There are lots of examples for like DevOps engineers, backend engineers, data engineers, data scientists, a whole bunch of different folks who sort of have their hands on keyboards. They may not know that they have optimization problems sort of that they can solve. But it's not an exhaustive list. We talked about 40 different industries and all these different problems and all this sort of thing. So don't think that that this is exhaustive. Its documentation help you write prompts a little bit more effectively, but it's not a reason to never learn how to formulate and code. You definitely need to still learn all of that. And it is a custom GPT that helps you focus on the problem description and is not a way to replace optimization modelers at all. To see how Gurobi AI modeling works, particularly the GPT part of it, we're going to dive into 2 examples, and of course we have to do a widget example. Why would we start with anything else? And then after that, I'm going to dive into a marketing mix optimization example inspired by a friend of mine. So we're going to dive into that shortly. But before that, I want to just say congratulations and thank you so much for taking all of this time hanging out with us and learning so much about Gurobi and mathematical optimization. And I hope this was really informative for you. And again, if you're going to get survey links, via email and everything like that, please let us know what you think was great, what we can improve on, what you want to see in any future iterations, because that stuff does influence what we do. So again, thank you so much, and now let's dive into some examples. So let's start using the Gurobi AI modeling assistant to solve our widget problem. I couldn't think of a better problem to introduce you all to this tool. So if you're looking in the GitHub repository, you'll see a couple text files. One of them is a widgets prompt text file. I'm going to be sort of slowly, bit by bit, pasting that into the chat here in a minute. But there's also a general prompt text file and a prompt template text file. And we sort of noticed that being explicit about this setup and saying here's my problem statement, here are my objectives, constraints, and data and everything like that, that was something that helped performance a little bit. So we encourage you to use that template, although it's not necessary, but it's definitely a little bit helpful. So let's get started with our problem statement, and I'm just going to copy and paste from here so you don't have to see me type and make many mistakes. So I'm first just going to paste in the problem statement, which says we make widgets. We have a set of production facilities that produce boxes of widgets and a set of distribution locations that will then distribute the widgets for sale. Each distribution center has a forecasted demand, and each production facility has a min and max number of widgets it can make during this period. We need to decide how many widgets to send from production to distribution locations. So that's a brief description of our transportation problem. We're transporting widgets. So the next thing we're going to do is just paste in our objective. We want to do this at minimal cost. We want to minimize the cost of transporting widgets from production to distribution facilities. And let's talk about our constraints. Paste those in. And we have our demand constraints, which is saying we must meet demand at each distribution location. And then we have production limits. We have a maximum number of widgets at each production facility we can make, and we also have our minimum, which is 75% of max production. So now let's feed in some data a little bit. And since we hard-coded data in our original notebook, let's sort of just hard-code this data in here. So we have our capacity for each production facility, and that's the same amounts that we had in our original notebook. And here is our demand for each distribution location. So we have our distribution locations and the corresponding demand. And then transportation costs. That's a little bit slightly more information. So instead of just copying and pasting, let's upload a CSV. This is the same CSV that is in the GitHub repository, and let's let it run. So what's going to happen is the first step is to install a Python wheel of Gurobi Pi. So that's going to happen first, and then that takes a little bit, but goes pretty quickly, all things considered. And then essentially it's gonna, if you attach a CSV or some other text file or some other data files, it's going to give a summarization of that in a minute. And then start getting into the problem description and getting into the formulation and doing that translation from problem statement to formulation and describing that transformation, and then I'm going to get back into the code. So here we sort of see the just a little bit of the cost data to make sure that it was read in properly. And here is our problem definition. So we need to model problem distributing widgets. Here's a formal outline of the model. That's great. We have sets P and D, and it lists the elements of each set, so everything seems good there. We have our cost parameters, our demand parameter, max and min productions, which are properly indexed. And here's our decision variables, xij, or the number of widgets to transport from production to distribution. And our objective is to minimize the total cost. Constraints, our demand constraint is set here. We're saying that we must meet demand exactly. This is a slight difference from the way that we modeled it initially, where we said that we must be greater than or equal to. That's sort of following the transportation problem paradigm archetype a little bit more on our end, but at this point, it's not much of a difference. And then we have our production constraints, the min and max. Let's build and solve. So again, it hard codes this data and produces a min production dictionary based off of the max. Transportation costs, and it sets our model up, adds variables, sets the objective to be the cost times the decision variable, and demand constraints, meeting demand, check. Our production constraints for each production facility, min and max. We must meet our min production, and we have our production capacity, And again, the min production was defined earlier. Optimize, and let's look at the results. So we have our good old log file. So the optimal solution minimizes the transportation cost at 1,704.89 units. Yeah, we didn't specify if it's dollars really. So units of cost, and then let's now let's check to see if that's right. I have the original notebook from Opti 101, and I added a line because I didn't have the cost printed out nicely there, but I ran through it and we extracted the values and printed out the total cost of 1,704.89. Great, that matches. So far so good. We didn't get a printout of the decision variables, I believe. Nope. So I'm just going to ask. Show the decision variables, decision variable values in a pandas data frame. Only include positive values. So let's take a look at the solution that we have. Baltimore is 19 and 116. Baltimore is 19 and 116 to Nashville and Richmond, respectively. Cleveland sends to Columbia, Indianapolis, and Nashville. Cleveland sends to Columbia, Indianapolis, Nashville, and Little Rock. So Little Rock 140 units, Birmingham is 80, Little Rock 140, Birmingham's 180, Charleston is 121 and 41 to Lexington and St. Louis. So far so good. Everything is exactly as we had originally modeled it. Just a lot quicker because we went through that first notebook. It took us a long time. We went through it very thoroughly to make sure that we understood optimization, but this also did a nice job of explaining all this other information to help you sort of understand how it all comes together. So that's really nice. So far so good. Awesome. Now let's also remember what we did at the end of that notebook. We also added in our first set of binary decision variables, and we had a particular scenario where the Birmingham facility, we had the option of possibly increasing its capacity. And we can increase the capacity by 25 or 50 widgets, but it cost 50 or 75 units. So we can also choose not to expand. So we want to see which one of these possible scenarios would be better for our overall cost. So here is the sort of little bit of text that we can add to that to sort of say, hey, let's model that problem. Let's see what happens. So it immediately recognizes, hey, I need binary decision variables. Maximum capacity is now updated. And it then also updates our potential minimum capacity as well, because that is based off of the, again, the problem statement says that you must produce 75% of the maximum capacity. So if we update the maximum capacity with one of these values, then the minimum capacity is also impacted. And it's sort of leaving everything else the same. Okay, adds the two binary decision variables. Lots of stuff stays the same. Demand stays the same. And here we go. So it says that we selected the Y25, so we want to expand by 25 units. Let's see what happens if we looking at the looking at the original here. So I'm going to run all this real fast just to make sure that we have everything. Expansion choice, it's optimized, it was there, but let's always, okay. Well, let's compare the objective function value for what we have here and what essentially ChatGPT produced. And it's I thought I said it's 1,702 and change. That's what it said, right? Oh, yep, it says total cost 1,702.49. Well, that's not exactly what we have here. Huh. Wonder what the issue is. Well, essentially what comes down to is that constraint that I sort of the difference in the model that I sort of glossed over before in the demand. And essentially what we need to what happens is now that we've introduced binary decision variables, the equality of demand versus the, let's go back up here to the original, the equality of demand that we have here versus the inequality that we had before is something that's important. So let's see if we can sort of highlight that a little bit. So here is the shipment values here. So we could sort of see the difference. And let's ask it to, does it print out the values here? So print the decision variables again. In a pandas data frame. Oops. Including, showing only, here's what I was talking about, me making lots of typing errors, showing only the positive values. And maybe I'll say, yeah, it should know to print the X to fit, because we already printed the, we already printed the Y decision variables. So let's take a look here. Baltimore is still one. So Baltimore now is different. Let's see. And let's actually add one line here where we take so we take the sum of shipment. That's 722 total things we're shipping out, total widgets. And let's ask, what is the total number of widgets sent or produced? Should be pretty straightforward. 703 versus 722. So this is something that's very interesting. The difference between our two models was, one was we needed to meet demand exactly, and in this example we are saying something less restrictive. We're saying you must meet demand, at least meet it, but you can throw in more widgets if you'd like. And now that we had binary decision variables, which are on-off switches, which are not, and they make sort of bigger things happen, what we've noticed is it's actually less expensive to manufacture more widgets to satisfy all of our rules, again, because we have this rule of needing to produce at least 75% of our capacity for each one. So we noticed that it's actually less expensive to open up, to expand the capacity and overproduce widgets than it is to meet demand exactly. So that's a nice little important sort of takeaway lesson here, something that I was sort of thinking like when I was running through this before. It's like, why is this happening? It's very weird. But yeah, that's the only difference in the model, and it did make a little bit of a difference. So important to so the lesson here is, if we really do not need to meet demand exactly, and it is okay for us to overproduce in your problem, then maybe those little types of things may be important to make sure that are generated correctly when you're using ChatGPT for modeling. So I think that's all I wanted to show for this example. So let's then move on to our second example, which is on marketing optimization. Moving on to our next example of optimization modeling with generative AI, we're going to look at a marketing mix optimization problem that is actually inspired by a text from a friend of mine who works for a marketing company, and it's like, I might have to do some optimization in the future. This is what it looks like. And I was like, hey, I'm going to use this as an example. And he's like, that sounds good. So what I did with this is I tried to not really mess with the information as much, to sort of make it sort of like this is a real prompt from someone who's not quite an optimization expert, but knows that they may need to try an approach like this. So if you look in the GitHub repository for the training session here, you'll see a text file called marketing_prompt. I'm going to do the same as I did before, sort of copy paste the prompt in bit by bit so we can go through it and see what all comes together. So the prompt is, I am tasked with building an optimization engine for marketing effectiveness platform. I want to be able to input a goal for the response variable, and the engine calculates the optimal input values subject to constraints on overall spending and marketing channel diversity. Boy, this problem is great for mathematical optimization. Anyway, the output should be to determine how much to spend on various marketing platforms and media types for a set of products. I did tweak this a little bit to make it align more to a data set that I'm using as sort of the placeholder for this problem. It is a data set that is on Kaggle, and I'll sort of show all that in a minute. Actually, before we submit this prompt, let's look at that. So here is the notebook file that's associated with this session. There's a couple links in there for the documentation that I was mentioning earlier before in the slides. The GPT the link is here. Here is the link to the source data. Here is the prompt template, which I think is again very useful. Here is the regression data. So this is a data set that I put together using building a bunch of different regression models for product, category, media type, and platform, coming up with the slope of that, and then also min and max spends based off the historical data. I think the min spend is the lower 25th percentile, the max spend is the actual max, and then there's this value n for the number of instances that we have in the data. So the product category, other, toilets, multiple, bath sinks, bath faucets. This is a data set about bathroom stuff, so maybe not the coolest data set, but still pretty good. Kitchen sinks, showers, bath, and we sort of see all the different media types. So is it social media, search engines, TV, and then particular platforms. The slope again is the impressions per dollar that we get via regression. And then again, min and max spend. And I also put, I'll get to this in a little bit, but how I would model the problem. So spoiler alert, if you're really fast, you could catch that. But so let's put this problem in, and or let's finish out the prompt and then see what we get. So we have our brief problem statement. Let's put in our objective to maximize the total number of impressions. So impressions, as I sort of mentioned before, are the metric of interest. And then let's talk about our constraints. The constraints, the overall budget is total spending must be at most this seemingly random number, but it happens to be from the data set, the average weekly spend. Again, I threw out a couple data points. They're a little wonky, it seemed, but and some only had like a couple like platform or media types or something like that. So I just got rid of a few that were that only had a couple data points, but this is the average weekly spend. The individual spending bounds, so if media type and platform is selected for a product. So if you select a particular media type and platform, then there are min and max spending restrictions. So those are the min and max spend values in the column that we saw before. And there's an impressions linear model. Again, this is estimated using the slope of the linear regression model, which is impressions per dollar spent. And data. We need to give it data. In the CSV file, has all the data you need. So let's attach that. And uploading, and let's go. So, oops, something went wrong. Regenerate. There we go. All right. See, even in optimization modeling with generative AI, maybe that's the next section for Hassan's talk about when modeling goes awry is, hey, if you're using generative AI and it just quits on you. Anyway, we see the typical process that we saw before. Let's install Gurobi AI. Again, it's going to do like, let's take a quick look at the data and then dive into the problem description, problem statement, formulation, and code. Perfect timing. As soon as I was done talking. So again, a quick display of the data. Again, we've already seen it. I didn't really go through the individual values all that much, but so we have sets and indices, products, we have media types and platforms. Great. We have the slope, min spend, max spend, total budget, B. We want to maximize our total impressions, which is the sum over P and M and T of slope times X, because X is our decision variable. Our budget constraint is we can only spend as much as our budget allows us. And spending bounds, min and max. Now here, if you were paying attention to what how I was talking about through the prompt, I was very, very clear about the if. And we can see that, maybe some of you expert modelers out there, which we all are kind of at this point, that this may be a little bit of a problem. I said, if something is selected, then there are min and max spends. This just puts min and max spends just by default. So here is I really like this problem because it's important to sort of be clear, even in this scenario where we have a very clear prompt and I'm giving a conditional statement, just sort of bypasses that that requirement of condition of, hey, we have a conditional statement on if we want to select this, then these bounds are there. Anyways, I'll come back to that in a minute. So again, we have our products, media type, platforms coming from the data, our slope, min spend, max spend. This seems like too much code for me but I don't know. It just seems like all this information would be a lot easier to get through, but that's just me. But anyways, it adds the variables. Let's see, for it for P and MT, yes, we have X. All right. And our impressions are through the slope and the spending bounds. So again, we already see that this is going to be a little bit of an issue, but everything else seems to be pretty good. Our verbal constraints, our verbal sort of our written prompt seems to be, I'd say that it followed things pretty much exactly outside of that one little uh, one instance. So this is where even if you're using generative AI, you need to have an idea of what's going on. And here is the solution. I'm not going to dive into it bit by bit. Um, but it is important to understand the the error here. So let's see what happens. So I asked if we spend if we decide to spend, and now there are lower bounds for everything, for each for some decision variables. Model the conditional statement. Probably could have asked it to fix it a little more easily, but let's use binary variables that activate or deactivate. All right, perfect. So let y PMT be a binary variable. There we go. And this is precisely what we want. We want to make sure that we put the if we decide to spend, then these things are active. If we do not, the y variable is 0, and the spend is 0. All right, so I think that that's where I'm going to leave it for now. I invite you to experiment with this prompt, experiment with other prompts, maybe add certain criteria to this problem now that we have binary decision variables that represent yes or no for each other decision variable, each continuous one. Maybe there are restrictions you want to add, other constraints you want to add, diversity constraints. That's one thing that was in the original prompt that we really didn't talk about, is adding diversity constraints. So yeah, go ahead and have fun with that, and test this out, and also look at the documentation. Take a gander at all those examples, and there is a survey link in the documentation. I probably mentioned this already, but I really would appreciate, and the rest of the team that helped work on this would really appreciate any feedback you have on the documentation. So I think I'm going to sort of end this session now, and thank you all so much for taking the time to learn how generative AI can help with optimization modeling. And I look forward to hearing about the problems that you try and solve. So thank you again so much for your time, and enjoy the rest of your day, the rest of your week, and hopefully we'll see each other, hear each other soon. All right, take care.